Hello, I'm Michelle Crummell, and in this lesson we're going to look at the first part of the Fundamental Theorem of Calculus, which is going to help us evaluate definite integrals. Now, to get us used to working with some of the notation we're going to see, let's work with the following summations. First, we want to expand the sum of f of k from k equals 1 to 5. So if you remember how the summations work, k equals 1 down here, and this is called the index, tells us our starting value for k. So we let k equal 1, and then we evaluate this expression here. So it's f of 1. And then we increase that index by 1. So now we're going to let k equal 2, and we evaluate this expression here, which would be f of 2. And each time we evaluate at a new value of k, we are adding that quantity. So it's f of 1 plus f of 2. Then we increase k by 1, and we let k equal 3, and we evaluate this expression. We're going to get f of 3, and then we're going to get f of 4, and then we're going to get f of 5. And when we get to k equals 5, as indicated by this upper limit here, we stop, and we find the sum of all of these values. Now, we don't actually have the equation for f of k, so we're going to leave our answer like that. Number 2, we have the sum of g of n from n equals 1 to 3. So we start at a value of n equals 1, and we evaluate this expression here when n equals 1. So that's going to give us g of 1. Then we increase n by 1. So now n is 2, and we evaluate this expression. We get g of 2 plus g of 3. And I'm going to stop there because n only goes up to 3 for this problem. For the next one, we have g of x sub I, and we're summing from I equals 1 to 4. So we start by letting I equal 1, and we evaluate this expression. So it's going to be g of, now I'm not replacing the x with a 1, I'm replacing the I with a 1. So it's going to be x sub 1, g of x sub 1, plus. Now we increase the value of I by 1. We're going to let I equal 2, and we evaluate this expression. We're substituting 2 in for I. Remember, not for x. So we get g of x sub 2 plus g of x sub 3 plus g of x sub 4, and then we're going to stop there because we stop when we get to I equals 4. And for the last one, we want the sum of f of x sub I minus f of x sub I minus 1 from I equals 1 to 4. So first we let I equal 1, we get f of x sub 1 minus f of x sub, now this, and it's a little bit hard to see here, but the I minus 1 is all in the subscript there. So when we let I equal 1, we get x sub 0. Okay, this is the first term when we expand this summation. Now we're going to increase the value of I by 1, so we're going to let I equal 2, and we're going to evaluate this expression here when I equals 2, plus. So it's f of x sub 2 minus f of x sub 2 minus 1, so x sub 1. Okay, plus, then we let we let I equal 3, so f of x sub 3 minus f of x sub 2. Okay, I see the pattern now, so I can go a little more quickly. F of x sub 4 minus f of x sub 3. So we're just here subtracting f of x sub 1 less than whatever this one was. Now we can simplify this a bit more. If we notice, for example, we have f of x sub 1 here and minus f of x sub 1 here, that's going to equal 0. And we have f of x sub 2 minus f of x sub 2, that's going to equal 0. And we have f of x sub 3 minus f of x sub 3, that's also going to equal 0. So we can simplify this to just f of x sub 4 minus f of x sub 0. And this is related to the following problem. We have a graph of a function f of x. We have a table of values giving us the f of x values for certain values of x. And we are asked, what is the net change in f of x over the interval 0 to 5? So remember that f of x represents a y value, and this interval here from 0 to 5 represents x values. So it's asking us on this interval between x equals 0 and x equals 5, what is the overall change in the y values? In other words, the change from the initial y value to the final y value, the y value when x is 0 and the y value when x is 5. What is that overall change, that net change? So we can do that in one step just by saying, well, okay, we started right here. When x was 0, y is something, I don't know. I do know because I can see it in the table. It's 2. So we have a y value of 2 right there. And then when we get to the end of our interval, when x equals 5, here, if we follow that up, then we are at, from the table I can see, 8.25. 8.25. So the overall net change in f is this distance right here, from 2 to 8.25. So 8.25 minus 2 equals 6.25. That is the net change in f of x on the interval from 0 to 5. So we could do that in one step just by looking at the y value where the interval begins and the y value where the interval ends and find the difference. Or we could also do it in smaller steps. We could say, well, on this little subinterval from x equals 0 to x equals 1, we get a change in y. It's pretty small, but there is a change in y there. And then on the next subinterval from 1 to 2, we get a change in y. It's about that big, right? And then on the next subinterval, we get a change. It's that big. And we get a change. It's that big. And then on the last subinterval, we get a change that's that big. And if we added up all of those little changes, we would get the same overall answer, 6.25, as the overall net change there. By breaking it down into subintervals, what I was really doing, so here's a subinterval, I was doing like the 2.25 minus 2 plus, and then the next subinterval, 3 minus 2.25 plus, and then this next subinterval, 4.25 minus 3, and so on. And we can see something similar is going to happen that we were showing in the last slide, where we've got plus 3 minus 3. And we have 2.25 minus 2.25. And all these little inside values are going to cancel out, and they're just going to leave us with the f of x value at the first endpoint. And then if I were to keep going, we'd have our 8.25, which is our f of x value at the right endpoint. So in general, we can express this in the following way. If we just want the change in f on the interval from a to b, we can say it's f of b minus f of a. That's doing it all in one shot. Or we can think of it as the sum of a bunch of net differences, breaking this down into subintervals, where our subintervals go from I minus 1 to I. So we start by letting I equal 1, and that would be f of x sub 1 minus f of x sub 0. And then we let I equal 2, and that would be f of x sub 2 minus f of x sub 1. So we get the net change on each of the little subintervals, and the summation here is going to add up all of the results. And so that's going to be equal to just the overall change, f of b minus f of a. Now, according to the mean value theorem, since our function f of x is differentiable, we know that somewhere within each one of our subintervals, the instantaneous rate of change at a certain x value, which we're going to just call c sub I, is going to equal the average rate of change on that subinterval. Okay, so we have f prime of c sub 1 equals f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. That must be true according to the mean value theorem. It's guaranteed. There's at least one place for which that is true. And then rearranging the terms of the equation, if we multiply both sides of the equation by the denominator over here, we get this result. Remember, this right here is just that net change on a subinterval. And we can say now that that is equal to f prime of c sub I for some value c in that interval times x sub I minus x sub I minus 1. Now we're going to make a substitution. Okay, so we have this equal to this. We're going to substitute. Okay, so right here we're making that substitution, which is going to give us this result right here. And as we saw in a previous lesson, this Riemann sum can be rewritten using integral notation. Now we wrote it slightly different in the last lesson. We wrote limit as n approaches infinity, and then we summed from I equals 1 to n, but it's going to produce the same result here. So we have f of b minus f of a being the net change of the function f of x on the closed interval from a to b equal to the definite integral of f prime of x dx. So this gives us another way to interpret a definite integral. And it leads us to the first part of the fundamental theorem of calculus. If f of x is continuous on the closed interval from a to b, then the integral of f of x dx from a to b is equal to capital F of b minus capital F of a, where capital F of x is the antiderivative of f of x. And as we just saw, this is going to give us the net change of the function big F of x on the interval from a to b. So in other words, if we integrate the rate of change of a function, what we're going to get is the net amount of change in that function. We want to evaluate the definite integral of negative 2x plus 3 dx from negative 2 to 1. And we're going to do this in a number of ways, and we should get the same result each time. The first way we're going to approach this problem is using the limit definition of the definite integral, which is what we studied in the previous lesson. So to set this up, the first thing I want to do is identify my delta x. And to do that, I'm looking at the upper and lower limits of integration here. The width of this interval is 3. The distance from negative 2 to 1 is 3. And so my delta x equals 3 divided by n. That's the total width of the interval, 3, divided by n, the number of subintervals, which gives me the width of each subinterval. That's my delta x. And then my x value, you can say x sub k, is my starting value, negative 2, plus k times delta x. So 3k over n. Now we're going to make some substitutions. We're going to replace the dx here with delta x. And then we're going to replace the x here with negative 2 plus 3k over n. So negative 2 times, now we're making a substitution, negative 2 plus 3k over n plus 3. Okay, so there's our function. We're going to multiply by delta x, which is 3 over n. We're going to sum from k equals 1 to n, and then we're going to take the limit as n approaches infinity. Now let's simplify algebraically. So I'm going to distribute the negative 2. 4 minus 6k over n plus 3 is going to actually make this a 7. And then I still have to multiply by 3 over n. So 21 over n minus 18k over n squared. Now I'm going to use some properties of summation. 21 over n is a constant multiple, so bring that outside. (18 over n squared is a constant multiple, so we will factor that out as well, leaving behind a k. The sum of 1 from k equals 1 to n is n. And the sum of k from k equals 1 to n is n times n plus 1 over 2. And then we can go ahead and take the limit here. So we've got 21, and then our leading term here is going to be 18n squared, and in the denominator 2n squared, so minus 9. 21 minus 9 is 12. So coming back up top, this definite integral here is equal to 12. Okay, so that is one method for evaluating this definite integral. Let's try a different way, and keep in mind that the answer should be 12. So we can also interpret this as the area under the curve y equals negative 2x plus 3 on the interval from negative 2 to 1. And that's the shaded area that we see in the graph over here to the left. So remember, when we say area under the curve, we really mean the area between the curve and the x-axis. So to find the area of this shaded region, we can use geometry formulas. We could break this up into well-known shapes. This is a 1 by 3 rectangle, so it has an area of 3. And then we have a half of a 3 by 1, 2, 3, 4, 5, 6. Half of a 3 by 6 rectangle, or you can say it's a triangle with height 6 and width 3. Either way, I think it's just mentally faster for me to say it's half of a 3 by 6 rectangle. So it's half of 18, or 9 for that area there. And when we add those two areas together, we get 12. So again, we get an answer of 12. That was a much faster way to work that out. Although if we didn't have the graph provided for us, it would have taken more time to graph it and figure out where we had shaded and then get the area. But a nice, quick, easy way to evaluate the definite integral here when we do have a graph and we can divide up the area into well-known shapes. So we're going to look at another method now, and it's going to be the theorem that we just learned about. Let me go back. The fundamental theorem of calculus says if we want to evaluate this definite integral here, we just find the antiderivative function, we evaluated that at the upper limit of integration, minus, and then evaluate that antiderivative function at the lower limit of integration. So let's try that. We want the antiderivative of negative 2x plus 3, and we can get that using our reverse power rule. So negative x squared plus 3x. And if you're not sure about your antiderivatives, remember you can take the derivative of your answer here and make sure you get back to what you started with. Okay, now the notation we're going to use here, normally if this was not a definite integral, so not a definite integral meaning we don't have an upper or lower limit of integration. If the problem looks like that, then we would put plus c as a placeholder for our constant term here, and that would be our answer. But when we have a definite integral, it seems we don't need to do that. Again, I'm following this theorem right here, which tells us how to evaluate this. It's f of b minus f of a. So what I'm going to do for this problem, I'm going to go ahead and write the plus c for the constant of integration, because I do always get that question, why didn't you write a plus c? So let's go ahead and put the plus c, the constant of integration. We're going to work this out, and then we're actually going to find that we don't need to write the plus c when it's a definite integral, and we'll see why here in a moment. But for this first problem, I'm going to go ahead and include it. So here's the antiderivative function, and you know what? Let me move this down here so that I can label it big F of x. Okay, and let's be super clear, coming from the fact that little f of x equals negative 2x plus 3. Okay, that's called the integrand, the thing that you're integrating. So if our integrand is negative 2x plus 3, then our antiderivative function here, the big f of x, is negative x squared plus 3x plus c. And according to the fundamental theorem of calculus, the answer that we're looking for is big F of 1 minus big F of negative 2. Right? This is the upper limit of integration, the b equals, and this is that lower limit of integration, the a equals. And we want f of b minus f of a. That's our setup here. Okay, so f of the b value, f of 1, I'm just going to substitute 1 into big F of x. I get negative 1 plus 3 plus c. And then for big F of negative 2, again, I'm just substituting in negative 2 for x. I get negative 2 squared plus 3 times negative 2 plus c. Let's simplify that. So we get negative 4 minus 6 is negative 10 plus c. Now remember, we have to do f of 1 minus f of negative 2. Okay, so here's f of 1. I didn't simplify that, but that's equal to 2 plus c. So 2 plus c minus, and then f of negative 2 is right here, negative 10 plus c. And when we simplify that, we get 2 minus negative 10 is 12, and we get c minus c is 0. So in the end, we do get 12 as the answer. What happened to the plus c? Well, we had a plus c in f of 1. We had a plus c. And in f of negative 2, we also had a plus c. And because we're going to subtract those two expressions, we're always going to have c minus c. And that c is always just, c minus c is always going to give us 0. And so it just disappears. So when we're evaluating definite integrals, generally we don't even bother to write down the plus c because we know that it's just going to cancel out in the end. Now I'm going to rework this problem using this method one more time because I did a lot of writing here. And generally when you're evaluating the definite integral using the fundamental theorem of calculus, you don't have to write down this much stuff. I just wanted to be really clear for our notes for our first time working through a problem like this. So I'm going to do one more time and show you a normal amount that I would write down and then a notation that I would use if I were evaluating this. So I would look at the integrand, negative 2x plus 3, and I would find the antiderivative for each of these terms, so negative x squared plus 3x. I'm not going to bother to write the plus c. What I am going to do instead, I'm going to put square brackets around this, and then I'm going to write my lower limit of integration down here and my upper limit of integration up here. And that is the notation we use to indicate that we have not yet substituted our upper and lower limits of integration into the antiderivative function, but we're about to. Okay, so the thing inside the brackets is the antiderivative function. And now I'm going to sub in the upper bound, the 1. Just substitute in the 1. So I'm going to get negative 1 plus 3 minus, and then I'm going to sub in the lower bound. So minus negative 2 squared plus 3 times negative 2, like so. And then we're going to simplify. So negative 1 plus 3 is 2, minus, and then in the other side of parentheses, we've got negative 4 minus 6 is negative 10, and that's going to give us 12. So that's the normal amount of writing that you would do for a problem like this when you're using the fundamental theorem of calculus. And this was a lot easier than the limit definition of the definite integral, right? It's a lot less to write down. You don't have to deal with summations. You don't have to deal with finding limits. It's a much quicker way to get to our answer, and it didn't rely on the graph. So the graph is a great way to get the answer in some cases. It's a quick and easy way. But you won't always have the graph provided to you, or maybe it's a complicated function and you're not sure what the graph looks like, or it's not going to give you triangles and rectangles where you can easily calculate area. So the fundamental theorem of calculus is usually the go-to way to evaluate a definite integral. Quick and easy. Now there's one more way that we haven't talked about. It's even easier, and that is to just use the graphing calculator. But of course, that's not always an option. So on your graphing calculator, you can evaluate a definite integral if you hit Math 9 on the TI-84 Plus, and then you just enter this as you see it in the template, and it should give you the answer 12. Okay, so we just evaluated this definite integral in 4 different ways, and we got the same answer each time. Let's take a look at this next problem. So we know that there are a variety of ways we can approach this, but I want to focus on using the fundamental theorem of calculus since that is the topic of today's lesson. So we're going to start by finding the antiderivative. And this is the same integrand that we had in the last problem. What's different about this one is the interval on which we're working. But the antiderivative, is going to be the same, negative x squared plus 3x. Our interval, however, goes from 2 to 5. So we always put the a value where the interval starts on the bottom. We use that number on the bottom. So we're going from 2 to 5. So you read it that way, from 2 to 5. Now we just need to substitute in the 5. So negative, and then 5 squared is 25, plus 3 times 5 is 15. Okay, so I'm subbing in the upper bound. Put parentheses around that. And then minus, now parentheses again, because here's where we're going to sub in the lower bound, and we want to make sure that we're going to distribute this subtraction. So now we sub in 2, so it's going to be negative, and then 2 squared is 4, plus 3 times 2 is 6, and we'll simplify so we get negative 10 minus 2, or negative 12. Now let's just look at the graph and see if it makes sense, if it's reasonable that our answer is negative 12. Well, the triangle that we have here is actually, or the trapezoid rather, that we have here is the same size and shape as the one we had before. It's just reflected. If I go back, here's the one we had before, so you can see it's the same size and shape, it has the same area, 12. But this one is below the x-axis, and we use signed area when we're evaluating definite integrals. So this has an area of negative 12. We say negative 12, meaning that the area is 12, but it's below the x-axis. Let's take a look at this next one. Again, same integrand. We're working on a different interval. Now we're going from negative 1 to 4. And visually, look at the graph and try and predict what you think the answer is going to be. So we've seen how we can interpret definite integrals as area. We've got the shaded area on the interval from negative 1 to 4. What do you think the answer to this problem is going to be? Let's go ahead and evaluate it using the fundamental theorem of calculus. So we'll sub in 4, the upper limit of integration, get negative 16 plus 12. Minus, now we're going to sub in negative 1, so minus negative 1 squared is 1, plus 3 times negative 1 is negative 3. Simplify, we get negative 4 minus negative 4, which is negative 4 plus 4, which is 0. Now, we don't have 0 area, but remember, when we are thinking about area below the x-axis, we use signed area. So we have the same amount of area above the x-axis and below the x-axis, and so they're essentially canceling one another out because one is a positive area and one is given as a negative area. So it makes sense that we got 0 as the overall answer here. Okay, the next one, same integrand, so the antiderivative negative x squared plus 3x. Our interval this time goes from negative 1 to 3. So we sub in the 3, minus, sub in the negative 1, and we get 0 minus negative 4, or just 4. And so in thinking about the area here, we've got some positive area, some negative area. So the amount of negative area is going to cancel out some of this positive area right here. So all of this is just going to be 0. The net area there is going to be 0. And then what we're left with is just really this shaded area right here, which is 4, positive 4. Okay, then looking at the graph here, you might be able to predict what we're going to get as an answer. But we can work this one out using the fundamental theorem. So same integrand, the antiderivative negative x squared plus 3x. But this time we're working on the interval from 0 to 5. So we'll sub in the 5 minus, then we're going to sub in the 0, which is just going to give us 0. And so the answer, negative 10. Overall, we have negative net area because the amount of negative area or amount of area below the x-axis is much larger than the amount of area above the x-axis. Okay, this would be a great time to pause the video and try some of these on your own using the fundamental theorem of calculus. We have different integrands here, so you get to practice finding your antiderivative functions, and then we are substituting the upper and lower limits of integration into the problem. So first one, antiderivatives, x squared and then minus x cubed over 3. We are evaluating from negative 1 to 2. Sub in the 2. Then sub in the negative 1. And simplify. And we get 0. The next one, we are going to find the antiderivative, so you might find it helpful to rewrite 1 over x squared as x to the power negative 2, use the reverse power rule, or you might recognize this, oh, that's the derivative of negative 1 over x. Now we have to be really careful here because it's easy to just kind of get lost in the math doing the steps and say, oh, okay, I can go from negative 2 to 3, and I can sub in the upper bound and get -1/3 minus, then I can sub in the lower bound and get a 1/2 and simplify and get an answer. But that answer would actually be wrong because the fundamental theorem of calculus does have a condition, a very important condition. Let's go back and look at the theorem. It says here, if f of x is continuous on the closed interval, that is a condition for using this theorem. We don't want to apply this theorem if the condition hasn't been met, and the condition is that f is continuous on a closed interval. Let's go back and look at our problem. Is 1 over x squared continuous? Well, 1 over x squared has a discontinuity at x equals 0, and x equals 0 is in the interval from -2 to 3, so that's a problem. Our function 1 over x squared has a discontinuity. It is not continuous on the interval from -2 to 3. So we cannot use the fundamental theorem of calculus here. It would be incorrect, and it will give us the wrong answer. 1 over x squared, let's say since 1 over x squared is not continuous on the closed interval -2 to 3, FTC, that stands for Fundamental Theorem of Calculus, FTC does not apply. Now, that doesn't mean that there's not an answer to this problem. It just means we can't find the answer using the Fundamental Theorem of Calculus. We may still be able to get an answer using one of our other methods, either using the limit definition of the definite integral, or thinking about it graphically, or even using Math 9 to try and get an answer numerically from the graphing calculator. But this type of problem is beyond the scope of this course. We do look at problems like this in AP Calculus BC. Let's move on to the next one. We've got the function 2x plus 3 over x squared. Now this one also has a discontinuity at x equals 0. However, it's not an issue because 0 is not in the interval from 1 to 2. On the interval from 1 to 2, 2x plus 3 over x squared is continuous, and so no issue there. We may use the fundamental theorem of calculus to evaluate this definite integral. So remember, there's no quotient rule for integrating. You can't just take the derivative of, or the antiderivative of the numerator and the antiderivative of the denominator. It does not work that way. We want to simplify this first and then find the antiderivative. So I'm going to divide 2x by x squared, and then I'm going to divide 3 by x squared. 2x over x squared is 2 over x. And then 3 over x squared, I'm going to write that as 3x to the -2 dx. Okay, so now we can get our antiderivatives. For 2 over x, it's 2 ln absolute value x. And then for 3x to the -2, it's 3x to the -1 over -1. So -3 over x. And we are evaluating from 1 to 2. So first we sub in 2, we get 2 ln 2 minus 3 over 2 minus, now we're going to sub in a 1. 2 times the natural log of 1, well the natural log of 1 is 0, and 2 times 0 is 0. So we get 0 minus 3 over 1 is 3. And simplifying this, we get 2 ln 2. We have minus 3 halves plus 3. 3 minus 3 halves is positive 3 halves. And that would be the exact value. Now, if we tried to check this one using Math 9 on the calculator is going to give us a decimal value. So if we need the exact value, we're going to have to work this one out by hand. And our fourth example here, so we'll find our antiderivatives. It's going to be x squared plus sine x. We're evaluating from 0 to pi. So we'll sub in pi. We have pi squared plus the sine of pi minus 0 squared is 0 plus the sine of 0, which is also 0. So we just get pi squared plus the sine of pi. The sine of pi is also 0, so we just get pi squared as the final answer. For this next set of problems, we're going to use a table to help us evaluate the definite integrals. So number 1, the antiderivative for f prime of x is f of x. We're going to assume that these functions are continuous because we have no way to verify that. And we are evaluating from 1 to negative 3. Now that may seem strange to say we're going from 1 to negative 3. It seems like we're saying that backwards, right? Because if you think about those numbers on a number line, negative 3 is to the left of 1. But we can go from right to left. That is possible to integrate from right to left, and that's all that this means. And we'll talk about how we can change that if we want to integrate from left to right instead here shortly. But it's not necessary to change it. We can still apply the fundamental theorem of calculus, assuming that we're working with a continuous function. So this is going to equal f of negative 3 minus f of 1. And we can read those values from the table. So f of negative 3 is 4, and f of 1 is negative 2, giving us a final answer of number 2. This time our interval goes from negative 1 to 3, and we're integrating f prime of x plus f double prime of x. So the antiderivative for f prime of x is f of x, plus the antiderivative for f double prime of x is f prime of x, and we are evaluating that from negative 1 to positive 3. So we sub in the upper limit of 3. We get f of 3 plus f prime of 3 minus, now we sub in the lower limit, f of negative 1 plus f prime of negative 1. And we use the table to evaluate. So f of 3 is 1 plus f prime of 3 is 3 minus f of negative 1 is 0 plus f prime of negative 1 is 1. So we have 4 minus 1, or 3. For the next one, the antiderivative of f double prime of x is f prime of x, and the 3 there is a constant multiple. So when you're taking the antiderivative, a constant multiple just remains in your answer. You can even factor your constant multiple all the way out of your integral if you like. So we're going to get 3. I'm going to go ahead and do that. I'm going to factor that constant multiple out. 3 times, and then the antiderivative for f double prime is f prime. And we're evaluating from 1 to 5. So we have 3 times, and then we sub in the upper bound, f prime of 5, minus, sub in the lower bound, f prime of 1. F prime of 5 is 2. F prime of 1 is 0. So we get 6 for the final answer there. And number 4, now we can split the integral into 2 integrals here because we have the sum of 2 functions. And I can also factor the constant multiple out of each one. So I'm going to do a couple steps at once. I'm going to factor out 1/2, and then we want the antiderivative of f prime, which is f, and we're evaluating from negative 3 to 3. Plus, now for this next term, okay, so I'm also applying the integral there. We are factoring out 2 as a constant multiple. The antiderivative of f double prime of x is f prime of x, and we're evaluating from negative 3 to 3. So it's like I separated this into 2 integral problems. Sub in the upper bound, we get f of 3 minus, sub in the lower bound, f of negative 3, okay, plus 2 times, sub in the upper bound, f prime of 3 minus f prime of negative 3. Okay, I'm going to move up here. So we've got 1/2 times f of 3 is 1 minus f of negative 3 is 4 plus 2 times f prime of 3 is 3 minus f prime of negative 3 is negative 2. So 1/2 times negative 3 plus 2 times 5, 10. So that's 10 minus 3 over 2, or 20 over 2 minus 3 over 2 is 17 over 2. Next problem, what is the equation of the tangent line to the graph of f of x at x equals 3? Now remember, to write the equation of the tangent line at x equals 3, we're going to need to know what is f of 3 and what is f prime of 3. And we can read that right from the table. So f of 3 is 1, f prime of 3 is 3, and so the tangent line equation is just y minus that f of 3 value equals the slope, which is the f prime of 3 value, times x minus our x value of 3, like so. Now use the equation of the tangent line to approximate the value of f of 3.1. So f of 3.1 would be like y of 3.1 minus 1 equals 3 times 3.1 minus 3. Okay, so y of 3.1 equals, I'm just adding this 1 to the other side, 1 plus 3 times 0.1. So 1 plus 0.3 equals 1.3. Now, we're not saying that f of 3.1 equals 1.3. Remember, I always say to highlight, circle, star, underline, exclamation mark when you see approximate or estimate in a question prompt, because we want to make sure we use the right notation. So f of 3.1 is approximately 1.3. Using our tangent line to estimate that value, we get approximately 1.3. Is this an over or under approximation? Well, I don't know if we can say for certain, but at x equals 3, so here, x equals 3, the second derivative is negative, which means that f is concave down at x equals 3. Okay, so at x equals 3, the graph of f is concave down. Let's just say this is where x equals 3, concave down. So our tangent line is above the curve, meaning it's going to give us an overestimate, but that's only true if the graph is still concave down at x equals 3.1. So we don't quite know that for sure, but if we are comfortable making that assumption, then we can say overestimate because f is concave down at x equals 3.1. Again, we don't know that for certain. I'd feel more comfortable if we had a little bit of extra information in the... Okay, now we're going to review some properties of the definite integral. We've already talked about this a bit before. If we have area above the x-axis, then that is going to be considered positive area. And if we have area below the x-axis, we're going to consider that negative area, or negative 1 times the area. And so if we integrate from a to b, and part of the area is above and part of the area is below, what we're actually finding is not the total area, but the net area. So we're going to get a1 plus negative a2. So that is the integral from a to b of our function f of x dx. If we integrate f of x dx from a to a, so this is a bit strange, right? We're integrating from a to a. Think about that as the interval that begins at a and ends at a. Well, what would the area be? If your interval has a width of 0, then there is no possibility of having any area, so you're just going to get 0. If you integrate from a to a, you get 0. So if you integrate from 5 to 5, from negative 3.1 to negative 3.1, whatever the number happens to be, if you integrate from a number to that same number, you're just going to get 0. This next property shows us how we can combine integrals. So if you integrate from a to c, so you're ending at c, and then your next integral begins at c, you can just combine this and do it all in one step. you can say that is just the integral from a to b, f of x dx. This also gives us a way to split up an integral into multiple integrals. So just divide your interval into subintervals and integrate on each subinterval, then add your... If we want to integrate from b to a, so here's one of those cases where we seem to be going from right to left instead of from left to right. You can integrate from right to left instead, from a to b, but it is going to affect your answer. And all we have to do to adjust for that is multiply the answer by -1. So I can factor that -1, which is a constant multiple, outside of the integral, or I could bring it inside of the integral if I wanted as a constant multiple as well. So if you want to flip your bounds, you get the opposite answer. A few more properties here. If b is less than a, so we just talked about this one. If b is less than a, and you're integrating from a to b, then we can rewrite that as -1 times the integral from b to a, f of x dx. So again, you can flip your bounds and then just multiply by -1. If k is a constant, so here k is a constant multiple, we can factor out the constant multiple. So we've seen that already as well. And then we used this third property also in the previous example. You can separate an integral. If you have terms that are being added or subtracted, you can split it up into multiple integrals. Use the same bounds. So this would be the integral of f of x dx from a to b plus or minus the integral from a to b g of x dx. If you're working with an even function, and in this example, I know this is an even function because it's symmetric about the y-axis. If you're working with an even function, then on the interval from -a to a, you're going to have the same amount of area to the left of the y-axis as you are to the right of the y-axis. So we can simplify the problem, and instead of going from -a to a, we can just say it's 2 times the area from 0 to a. And that can make the problem a little easier because it's generally easier to substitute in 0 for x than it is to substitute -a in for x. Not always, but a lot of the times that's true. If we have an odd function, and this one I can see that the graph in this example is odd because it's symmetric about the origin. If we rotate 180 degrees, the graph looks the same. So this is an odd function, and for odd functions, we don't get 2 times the area on the right half of the interval. We actually end up with just a result of 0. We can see that we have the same amount of positive area on the right as we do negative area on the left. And so we're just going to get a result of 0 if we integrate an odd function from -a to a. Let's try working with some of the properties we've just talked about. So we're told here that the integral of f from 0 to 3 equals 6. We've got that. The integral of f from 0 to 3 is equal to 6. And the integral of f from 3 to 7 is equal to -8. What is the integral of f from 3 to 0? Well, notice that's almost the same as this. The bounds are just flipped. And so we know that's equal to negative whatever this integral was, which was 6. So the answer there is going to be -6. The integral from 0 to 7. Well, to get from 0 to 7, we can start at 0 and go to 3. And then, right where we leave off at 3, the next interval starts at 3 and goes to 7. So if we just add these two integrals together, we get the integral that starts at 0 and ends at 7. So it would just be the 6 plus the -8, or -2. The integral from 3 to 3. Well, f of x from 3 to 3 wouldn't have any area shaded, right? So it's just going to be 0. F of x from 7 to 3. So we're just flipping the bounds on this one. If you want to flip the bounds, you multiply by -1. So it's -8, or just 8. Number 5, okay, we have to be careful here. We have information about the integral of f from 3 to 7, so we can get it from 7 to 3. The 3 is a constant multiple, so we need to multiply that answer for the integral of f from 7 to 3 by 3. But the 2, however, we don't have information like already given to us about what's the integral of 2, so we have to do that part by hand. The antiderivative of 2 is 2x. So we've got 2x, we need to evaluate it from 7 to 3. Plus 3 times, and we know what the integral of f is from 7 to 3, it's 8. So we did that right here. Okay, so we've got 2x, and the 2 is a constant multiple, so you could factor that out here if you want to. I'm going to go ahead and leave it in. So we've got a sub in the upper bound, we get 6, minus sub in the lower bound, we get 14, and then plus the 3 times 8, so we get 16. If f is an even function, what is the integral of f from -3 to 3? If it's an even function, we can just take twice the integral from 0 to 3, and that's given to us up here. That's twice 6, so 12. If f is an odd function, then the integral from -3 to 3 is just 0. That's always true for odd functions. If you're integrating from -a to a, you're going to get 0. In this next example, we want to find the integral of f of x, which is the function that we see in the graph here. And we're starting with the interval from 0 to 3. So we're going to use the method of finding area under the curve. From 0 to 3, we want this area here. And I can split this shaded region into a quarter of a circle and a trapezoid, or I can split it up even more and say a rectangle and a triangle and a quarter of a circle. So the rectangle is easy. It's a 1 by 2 rectangle. It has an area of 2. Then the triangle is half of a 1 by 1. So it has an area of 1/2. The quarter circle is 1/4 of the area of the whole circle that has a radius of 2. And a circle with a radius of 2 has area pi times 2 squared. So that has an area of just pi. Let me go ahead and just write pi there for that quarter circle. It has an area of pi. So the integral from 0 to 3 is just going to be the sum of that is pi plus 2 plus 1/2 is 5/2. So pi plus 5/2. Now the next integral goes from 0 to 4. So we already know the area from 0 to 3. The area from 3 to 4 is going to be -1/2. -1/2. And so this positive 1/2 is going to cancel out with that -1/2 there and just give a net area of 0. So all we're really going to have is the pi and the 2. So pi plus 2. The integral from -3 to 3. Now this is an even function. It's an even function. So I have the same amount of area from -3 to 0 as I do from 0 to 3. And I already know what I have from 0 to 3, so because that was the answer in number 1. So we just need twice that. Twice times pi plus 5/2 is 2 pi plus 5. And our last example, if big F of 0 equals 5, so f being the antiderivative of little f of x, if big F of 0 is 5, what is the value of f of 3, where f is the antiderivative of little f? Okay, so we want to set up our own definite integral here, and we know the value of f of 0, so we want that to be one of our limits of integration. We're looking for the value of f of 3, so we want that to be the other limit of integration. So I'm going to set up the definite integral to go from 0 to 3. Because I know that's going to equal big F of 3 minus big F of 0. And the integral of f from 0 to 3 we calculated as 2.5 plus pi equals big F of 3 is what we're trying to solve, minus, and then big F of 0 we're told is 5. And that means that big F of 3 equals, if I just add 5 to both sides, pi plus 7.5. if big F of negative 2 equals 3, what is the value of big F of 2? So again, let's set up a different definite integral, and we want to use this time negative 2 and 2 as our limits of integration. Negative 2 to 2. Because we know that's going to be big F of 2 minus big F of negative 2. So the integral from negative 2 to 2, this is an even function, so it's going to be twice the area from 0 to 2, which is pi plus 2. Then big F of 2 is what we're trying to find, minus big F of negative 2 is 3. We can add 3 to both sides, so we get 3 plus 2 pi plus 4, or 7 plus 2 pi. Okay, that concludes our lesson on the first part of the fundamental theorem of calculus, and a few lessons from now we will revisit the theorem and look at part 2 of the fundamental theorem of calculus. See you next time.